about this, this doesn't look like it's focused. Can anybody see that in here? Well, sort of. Okay. Well, basically, the idea is as such. You've heard about the issue of toxicological studies, hazard ranking, but that's just part of the story. We need to understand that exposure is an important part of it, and if there is exposure and there is toxicity to worry about, then we have to think about what are the implications. Now, what are the implications from the viewpoint of making decisions how to reduce such risk? And so in this diagram, basically what we're seeing is that what are the things that we can do? Well, design better materials, which means either use raw materials, different raw materials, if we see that a certain material is problematic, maybe change the processing and manufacturing, maybe put limitations on emissions from processing, regulate product use and disposal, and of course, in this process, in order to know if there is an issue with regard to exposure, we also need to be able to monitor. If we can't monitor, then we may have to make reasonable predictions. Okay, yesterday we heard in one of our speakers in the area of decision analysis says that we need to make assumptions. It took me a while to figure out that what he really meant by assumptions is that we have to have models. So some people think about models as basically assumptions, others think about them as the gospel truth. But whichever one it is, we need to figure out what those exposures might be. Now, from a decision maker viewpoint, you might need to go through an initial screening to just think about is there exposure likelihood, and if there is, you might then ask what are the potential hazard, and if, what happened here? And if there are hazards, then you might say, well, is there, let's quantify the exposure, and then you go through a decision process. Or, if in your initial screening you decide that either exposure is not likely to happen, or hazard, is not likely to be an issue, then you may short circuit all of this and go directly and ask, is there an impact? And if not, then I can make a decision with respect to whether the particular nanomaterial is problematic or not. So now, let's move forward into the more detailed picture. Some of you have seen that before, and I'm going to say the following. You've got hazard identification, you've got an exposure assessment. So if you're doing hazard assessment, one can ask the question, so what? What are we going to do with all of this? If you're doing exposure assessment, so what? What are we going to do with all of it? How are we going to combine it? So somehow we have to combine both of these into an environmental impact assessment that can lead to decision analysis. And part of what we do at the CEIN, at Theme 6, I don't dare to say that I'm a Theme 6 leader. After about almost 5 years, I think that I'm more of a Theme 6 servant. And what we're trying to do is really develop tools that can be used by decision makers so they can make informed decisions. I'm not going to say that they're going to make the right decisions, but they will make informed decisions. So I'll give you a few simple examples of what goes into doing that. So first, I'm going to argue that we have to think about it from the decision maker viewpoint. We have government agencies such as NIH, NIHS, we have CDC. What do they deal with primarily? Anyone? It's going to be a quiz afterwards. What do they deal with primarily? They deal with the issue of health toxicity of materials. On the other hand, we have the Environmental Protection Agency. What do they deal with primarily? What do they regulate? They regulate releases, they regulate concentrations in effluents. So one regulates primarily exposure, the other regulates or deals primarily with the issue of toxicity. Well, it's not that simple, but I'm going to try and simplify it in that way. Now you might say, well, wait a second, doesn't EPA also regulate on the basis of taking some toxicity information into account? The answer is yes, they do, okay? But they will make regulations sometimes without toxicity information based on the best available technology for treatment. And based on that, they will set the regulations. So we have to take that into account. And we have to be able to figure out exposure and toxicity. So I'm going to talk first about exposure. So in terms of exposure, a little plug-in. Those of you that have signed up for the work, did we call it, not a workshop, but the hands-on, the interactive session discussion. There will be two tools that you'll be able to play with. One, to assess the distribution of nanomaterials in the environment. It's based on a model that has been developed here over a number of years. And another one is to analyze high-throughput toxicity data. So in terms of this approach, what is it that we are interested in? We need to know if the material is released to the environment, whether it's the atmosphere, to water, to soil, where does it go? Because it will distribute itself. The environment, or let's say the atmosphere, doesn't know that it's supposed to be segregated from air or water, and vice versa. Water interacts with soil, interacts with sediment. So we have to take that into account, and we need to understand that there are mechanisms that lead to transport between compartments, between air and water, between soil and air. There are different mechanisms that lead to nanoparticle movement. Now, when we deal with nanoparticles, we have to understand that they are of different sizes. So why size is important in the environment? Those of you that live in Los Angeles know that after there is a rain event, you know, Los Angeles is beautiful and we can see the mountains, you know, very nice and clear. In part because rain scavenging is so efficient in removing particulate matter. And the efficiency by which particulate matter is removed depends on the size distribution. So I won't go into the theory of how that is impacted. The same way, if we deal with the issue of particulates in aquatic systems, their deposition will also be impacted by size. If we deal with the issue of wind resuspension, particles that are already on the soil, their reintroduction into the atmosphere is going to depend on their size and size distribution. If we deal with particles that are being intercepted by plants, by buildings, by surfaces, the efficiency by which they are collected is determined by their size distribution. So we need to understand that this is quite different from chemicals or from the chemical world, where transport and partitioning is very much impacted by thermodynamic equilibrium partitioning. In the case of particles, particles care less about thermodynamic partitioning and constraints on driving forces for transport. So once you take that into account, I won't belabor the modeling approach. Those of you that in the afternoon will like video games, you can come in and use this type of model, which basically allows you to develop various scenarios to ask, if I allow a nanomaterial to be released in a certain level to air, water, or soil, I can then calculate, using this model, what will be the concentrations and mass distribution in the environment. So this is an example for TiO2 for the Los Angeles area, doing estimation of emissions based on population, scaling the emissions based on population. What you find is that much of the material will be contained within the soil environment. So what Trish was just telling you a few minutes ago about the impact of nanomaterials on plants, basically there's a lot of merit to looking at that, because it means that if we release materials to the atmosphere, yes, we might have an issue of inhalation, but also a lot of those materials may end up in the soil. We can determine concentrations, and I won't, again, belabor that. You'll see sort of fluctuations in here. This is for LA, simply because there is rain. So when there is rain, concentrations in water will decrease, and then, will increase, and then it'll go down, and so on and so forth. And the same with the atmosphere, as you can see here. So as soon as there is a rain, there is a drastic decrease in the concentration. Rain ceases. If emissions increase, the concentration builds up again. You can determine the distribution of the nanomaterials, both in the water, in the atmosphere, which is, again, important for assessment of their impact. You can look at their distribution as a function of emissions. Now, this is kind of interesting, because it says, even when 10% of the emissions, in this case TiO2, is to the air, 60% of the total mass will be in the soil. Which means that you really have to go to a very low level of emissions before you can say that there isn't a significant impact on the soil. And you can see in the water in here, of course, here the emissions are distributed between air and water, so you can see as we decrease the emission in air, of course, the concentrations in water will decrease in that level. Now, what can you do with any of this? This is an example of just exposure-based ranking for Australia and for Switzerland, based on information that has been reported, one by an industrial source, another one by a government source, which basically looks at a number of different nanomaterials, and you can see the concentrations in the aquatic environment. So you can see in this particular case in Australia it's higher for SiO2, and you can see that for Switzerland it's you can look at the ferric oxide and you can look at titanium oxide in here, it's about the same. That by itself doesn't allow you to make decisions that incorporate toxicity. So the next question is, how do you take toxicity into account? There are different ways, and I'll just show you one. If you know what the maximum allowed concentration, you can take these concentrations, divide them by either the EC50 or you can divide them by the maximum allowed concentration, and you have a risk type index, if you will. So, one of the problems is, of course, there is uncertainty here. It's the uncertainty primarily here is in the source release data. You notice that I didn't say that the uncertainty is in our model. Okay. And that's where expert judgment comes into play. But in all seriousness, this is an important issue that we have to deal with. And I'm not saying it just to be funny, but we have seen that there is tremendous variabilities in what is being reported as production rates and emissions to the environment. In fact, there are even reports that have tremendous errors in them by orders of magnitude. But that is for another time. So now, how do we bring toxicity into account? I'll try and go through it very quickly. You've already heard about high throughput, low throughput screening. From my viewpoint is, you have all this data, the question is, how can we assemble it to make some reasonable predictions with regard to toxicity? So Andre's already showed you this, but very quickly, what it amounts to is that we have a lot of information about toxicity measures, whether it comes from high throughput, low throughput. There are data that includes controls, there is positive controls, there may be negative controls. You have to make sense out of it. And primarily this is important because in the realm of doing toxicity measurements, you'll find a few hits and there'll be a lot that are no hits. And so the statistics becomes very important in terms of pre-processing the data, exploring it for heat identification, then visualizing it to understand if there are patterns, and then to develop models that allow you to predict activity, bioactivity or toxicity, whatever it is that we would like to use as a metric in this case. So I'll skip through that and then, well, actually a little plug-in here. In the afternoon session, you'll also be able to look at a tool that allows you to, in fact, look at data, whether it comes from high throughput or low throughput, but any data can be put into a matrix format. You can actually analyze using our web-based tool to both cluster the data using self-organizing maps, using standard hierarchical clustering. You can apply various outliers removal. You can use normalization, various statistics to identify hits or, let's say, significant bioactivity, whether it's above, whether it's upregulation or downregulation. I don't know what's going on with this system in here. Okay, here we go. So I'll go through this. And again, the data could be numerical data, or the data itself could be data that is generated from imaging that was mentioned earlier. And so in terms of data analysis, of course, one has to speed up such data analysis. And at the CEIN, we've developed automated methods of phenotype recognition for such systems. I'll think that I will skip that because we're probably running out of time. But this gives you a map of this tool that I've just described that you'll be able to see. So you'll be able to analyze, look at raw data that comes from high throughput plates, be able to select from different type of analysis methods, some that are standard in the literature, others that have developed here. You'll be able to clean the data. So this is the case of looking at a number of metal and metal oxides. So now the data is being cleaned, and what you see are basically just the hits, okay, in the data. So you can sort of see it clearly. Now, of course, the task is how do you take all of this and actually develop models for that. I'm not going to go through that today. But what I will show you are just two slides that show something interesting. This is from work that we have recently done, and this is with basically ferric oxide type nanomaterials that are modified in different ways and are used for imaging. And in this particular case, if you look at all the data that is based on various cellular assays, there are 4 different cell lines, different concentrations, and you just do what is called self-organizing map analysis. Basically, you see clusters in here. So just pay attention to this cluster in here, C2. This cluster contains 2 nanomaterials, NP24 and 25 in here, and those are materials that in fact are approved for use in in vivo imaging. So without knowing really much about the toxicology, the question that you may ask, well, I mean, we know about all the toxicological data, but you may ask yourself, well, if this had been improved and I identify this cluster that now contains these particles, does that mean that all the other ones that also fall in here might also, be particles that we might accept as also being reasonable for in vivo imaging? Now, the answer might be, I don't know, but what you do know is that perhaps you narrowed the field from having to test all these particles and then say, well, let's just look at these ones in here that we identified. So that's one interesting approach that you can use when you look at such analysis. The other is to look at what Andre termed here as SARS, or structure-activity relations, or as what I call here quantitative structure-activity relations, which basically means, in this case, we may have regressions that allows us to actually predict EC50, okay, directly. On the other end in here, we may have classification that allows us to say, is it toxic or is it not toxic? But not only that, but to be able to say, what is the probability by which we can say that a given material is toxic? So in this case, I'm looking at the metal oxides that Andre described to you, and this is, again, work that is currently, sorry, this is, I said small in here, this is actually in nanoscale, currently in press. But basically, this is a map that shows us, it's a probability map. So, hot, means hot, okay, it's toxic, blue, cold, non-toxic in here. And this is a graduated map, so you see all the materials that have been identified as toxic are in here, and we can actually know the probability. Here we're expressing the probability by which we can say that a material is toxic. So if it's up at the top here, very red, we can say yes, 90%, 100% that we would classify this material as toxic. Now you see lines in here. Well, those lines are important because if you're a regulator, you might say, oh, I really don't care if a material is declared as toxic or non-toxic, or I'll accept both in the same way. Okay, so I'll accept errors both ways. This will be this line in here. And so you see here, you have copper oxide sort of on the verge. Okay, and you see the same thing with manganese oxide and nickel oxide in here. Sorry, in here, you see that they're all in here. On the other hand, if you say, I am not willing to do that, but I want to increase the penalty that one would pay if we classify materials as false positive, then basically you shrink, okay, this area in here, and you avoid declaring materials that would be declared as false positives. On the other hand, if you say, no, I really want to be overprotective, then I want to increase the penalty on false negative. Then this area is enlarged, and now you see that we would classify those guys in here. You see it in blue. That would be classified as toxic with a certain probability. So that would be a false positive, okay, in this case. But if you're a regulator, that might be okay. If you're, you know, someone who is in industry and care about making, you know, large-scale production and it affects your economy, you don't want to make that mistake. So it all depends on the decision that you make. Now, finally, what I'd like to say here is that the dotted line is basically the energy band gap that Andre has shown you, and what you see plotted in here is the hydration energy for the metal ion and the metal oxide. So what you see is that there are two factors in here. Again, it corresponds to the idea that Andre talked about, which is the solubilization of the metal ion. You see that having a material within the band gap is not a necessary, neither sufficient, you know, conditions for the material being toxic. However, it's a very strong indicator. At the same time, if our hydration energy moves in this direction, a low negative hydration energy, then it also means that the material is going to be more mobile, or the metal ion will be more mobile. So, mechanistically, it may make this material more available, or the metal ion more available, and there is enough in the literature regarding toxicity of metal ions that deals with their solubility and hydration energy that, in fact,